Hello everyone, David Ostrowski here again, Data Structures, CIS 2534, and in this recording I'm going to be covering additional content in support of our Chapter 6 material. Here, once again, we're going to take a look at the priority queue. We're going to go into some of the other variations of the heap structures as described in our text. And here in the beginning with this content, it's somewhat of a review, but hopefully it'll give you a little bit more insight every time we make a pass at it. So here they talk about, excuse me, uses for priority queues. Again, in many applications, schedulers would be applying a priority queue. And there's a lot of queues that exist in the real world that could be automated or not automated. Okay, you can consider in the context of bank tellers is typically a first in first out. With grocery stores, you could consider the fact of the lines that have less items. Okay, it's going to be assigning priority, right, on two levels. One is to having less than 20 items or 10 items or 7 items or whatever the case may be, as well as a function obviously of the first in first out. So the tie-in with algorithms, so that gives you a real world support or idea of exactly how they work, right? In most cases, there's more sophisticated policies, okay, in terms of operating systems, okay. If you take an operating systems course or if you plan on it, queues are fundamental, okay, or foundational type of concept. Here we look at routers or packets. They use priorities on data packets, file transfers, and streaming videos, and latency requirements. Processors also process jobs insert in context of multitasking and multiprocessing. Okay, they're going to be applying priorities as well. So in many of these cases, you're going to be relying on these fundamental concepts of a priority queue, and obviously it's going to be in a much more refined form, as they mentioned. So let's move forward here. So again, hopefully you can have an appreciation of the concept of abstract data type. You know, when we see, and I mentioned this before, right, when we look at heaps, a heap is not a priority queue and vice versa, right? But when we describe, that's why we use abstract data types, right? Because we describe it at an abstract level, and the heap is a natural means of its implementation, okay? And it can reside underneath, obviously, to do priority queue or any of the real world examples that have been mentioned. It's very easy to just simply make the assumption that you know, you could use an array and nothing more, or any type of list-based data structure. Okay, they're just not going to be as efficient, I should say, to implement. It'd probably be easier in most cases, right? But this motivates the ADT and the concept, because we make the distinction between a heap and a priority queue, and just about every book mentions them in the same context, which would lead you to believe that they're the same, but they're not the same. They just the heap lends itself well to the implementation. Why do we know that? Okay, because of our consideration of an algorithm analysis. That's where it comes in, right? So priority queue, ADT, okay, a set of elements with priorities or keys. A lot of the basic operations would be an insert or a delete. You could be either deleting a min or max. We went through this before, right? You could have the opposite of a min tree would be a max tree, I'm sorry. And with a priority queue, you would have a find operation, okay? And also you have increase, decrease key, remove, or new queue. So this is interesting. Okay, that again, we're describing it as a abstract, and we can have anything underneath it. Okay, we don't have to. We don't talk about array implementations, right? Because it's going to be a big event. We know that. Let's move forward. Okay, so some of the implementations, you can use an unordered linked list. Here, the insert is big O1, delete min would be big O-N, right? An ordered linked list, the min would be 0, 1, the insert would be 0, 1, or 0n. And a lot of this is in terms of the choice between your data structures, there's trade-offs here, right? A lot of it can be, you know, how static is my data structure? Am I going to keep on adding to the data structure? If I am, then in that case, I would take that in consideration, that I don't have to keep on doing that operation. But you have to factor in the idea that you have to sort it. If I did very little sorting, if I only sorted it once, I didn't have a lot of modifications to my associated data structure, then it's going to make a lot more sense to me, right? So moving forward, if I look at a binary, balanced binary search tree, the insert or delete min would be big O log n, increase key, decrease key, and remove would also be big O log n. Union would also be big O of n, right? Most implementations, they're based on heaps, okay? And again, we motivate that from an algorithm analysis standpoint. So the heap ordered binary tree, the tree structure is a complete binary tree, and we have one element per node. Here only vacancies are at the bottom and to the right. The tree is filled level by level, and such a tree with n nodes would have a height of big O log n. Heap ordered binary trees, a heap property would include one element per node. Here the key of the parent is less than the key of the child at all nodes everywhere. We went through this. Okay, the min key is at the root. So we look at the comparison here. I have 13 going to 21 and 16. Okay, and 13 is less than 21. It's also less than 16. 21 is less than 24, 31. 24 is less than 65, 26. 31 less than 32. The second tree to the right, however, and this is indicated right by the dotted line, I have 13 going to 21, 16. Okay, fine. 21 goes to 6, so I have a min. I have a node with a parent is less than a child is parent, so it can't be either trees, can't be min or max trees. That's violated by 21. Okay. So how do we manage that? Okay, and this kind of comes down to the properties. You would switch the values. However, you have to do more than one switch, right? That's what we call as percolate or bubble up, right? Well, the key is less than the parent. I'd swap the E with the parent. Okay, so 6 and 21 would be switched, and correspondingly the 6 would be switched with the 13. I can't remember if it actually addressed it in the slide. Correspondingly, some of the basic operations for increase or delete min, you would have a percolate down. So the key, well, the key is greater than the key, some child of the E, I would swap E with the smallest child. So in terms of decreasing or increasing the key, you need to know where the element is. There's no find. Okay, the decreased key, the key of element would be equal to the key element minus the amount. Percolate up. And with increased key, the key of the element equal to the key element plus amount, I would percolate it down. With insert element, I would add the element as a new leaf in a binary heap. The new leaf would go at the end of the array, percolate up the element, and I have a big O tree height equal to big O log n for binary heaps. So let's look at some examples here. If I look at the binary heap example, insert 14, I would add a new leaf, then percolate up, and you would finish the insert at the end of the example, right? So you would insert 14 of the empty circle here, and then be in change with 31, and then in change with 21, and then as a min, I believe this was a min heap, right? Then I would be done there. That's how I make the operations. With delete men, the element would be returned is at the root, and to delete it from the heap, I would swap the root with some leaf. In a binary heap, this would be the last leaf in the array. I would percolate down to the new root, and then I'll make the comparison of big O to the tree height equal to the big O log n for the binary heap. Delete men. Here I would have a hole at the root, right? I would remove that. Then I would put the last element in it, and then percolate down appropriately. Okay. So I can't exist in this format, and I would have to, after deleting 13, right? I have to perform the operations to reattach that tree. Array representation of binary heaps, so it can be visualized as a tree, but it can be easier to implement in most cases as an array. So I can use index arithmetic to compute the positions of parent and children instead of using pointers. And again, this is a design decision. Do it either way. Obviously, if I represent it as an array, then I'm going to have some efficiency in being able to do that. So here I can look at A, B, C, D, E, F, G, H, I, J, and they're just numbered appropriately. And I know if I'm following the properties of my heap, and I'm always going top down, binary tree, left to right, and I don't have odd children in that respect. Let's see if I can. Whoops. So here's a shortcut for perfectly balanced binary heaps. In terms of the array implementation, I would have 2 times the parent, give me the left child, and 2 times the parent plus 1 would give me the right child. And correspondingly, the parent would be the child. And these are the indexes, right? I take the appropriate index. I have 1, 2, 3, 4, 5, 6, 7. So if I have 4, for example, and I would have 2 times 2 is going to give me 4, right? And 2 times 2 plus 1 is going to give me 5 appropriately. If I have 4, I'm going to have 2 times 4 is 8. It's going to be the 8. And the right child would be 9. We can try it over here. 3 times 2 is 6. 3 times 2 plus 1. Correspondingly, if I have 7, and if I divide it by 2, and I take the round it down, okay, indicated by this, and it's going to give me the associated array reference. So it's really, and again, I think one of the things to grab here, we're always gravitating towards more sophisticated data structures. It's not necessary in some cases. Here, we're relying on a just a simple array-based implementation. Hey, if you can use an array, use it. It can. It's always better, when it's, you want to make your design as simple as possible and not any simpler. It could be a hindrance to make it more complicated than it has to be, right? So heap, sort of, build heap. I have a naive method for sorting with a heap. Here I have an insert and delete min operation that would come to the analysis of big O n log n. Improvement here to build the whole heap at once. Here you start with rate and arbitrary order, and then fix it with the following routine. Template class comparable. I have a binary heap of the comparable type, build heap, and then I take the current size and support the percolate down operation. So build heap, fix at the bottom level, and fix it to the next bottom level, and then work your way up to the top. Analysis of build heap. For each I, the cost would be the height of the subtree at I. And for perfect binary trees, you perform the operations here to get the sum, and you'd have big O of n. Summary of the binary heap operations. Insert, I have big O log n. Delete min, big O log n. Increase key would be big O log n. Decrease would be big O log n. Remove would be big O log n. And build heap would be big O n. The advantage, right? The simple array representation of pointers. If you can get away without relying on pointers, again, as I mentioned, you're always, just make it that much easier. And here the union is still big O of n. Okay. Some applications on extension of binary heap, like the heap sort. Graph algorithms may rely on binary heaps, first path, MST. Event-driven simulation, tracking top K items on a stream of data. Also D-array heaps. Insert operation would be big O log D of n. Delete min would be big O D log D of n, and optimize the value of D for insert / delete min. Leftist heaps. These are also known as mergeable heaps. So one thing to note, and motivation for this type of implementation, is binary heaps. They are great for insert and delete min. However, they do not support merge operations. Here, leftist heap is known as a priority queue data structure that also supports the merge of two heaps in big O log n time. Leftist heaps introduce an elegant idea, even if you've never used merging. There's several ways to define the height of a node in order to achieve their merge property. Leftist heaps, they use MPL node path length, a seemingly arbitrary definition of which the intuition will become clear at a later point in time. Right? Leftist heaps, the length of the shortest path from X to a null pointer is MPL X. A leftist heap is known as a heap ordered binary tree in which the MPL left node of X is greater than or equal to NPLI, the right child of X, for every node of X. Therefore, the MPL X, the length of the right path from X, also MPL root, is less than the log of n plus 1. Proof of that would be leveraging induction to prove that the MPL root equals R. This implies a tree has at least 2R to the -1 nodes. So leftist heap, MPL X, the length of the shortest path from X to a null pointer. And here they identify the two being leftist heaps, or which one is valid, okay? and we go back to our let's go back to our properties here. Okay. Wanted to point to that I didn't have a